Friends, welcome to my hospital room. I know the one question that's probably on a lot of your minds is were there hospitals in Uruk, the ancient city, 5th millennium BC city that we talked about last week, associated with Gilgamesh, all that stuff. And though I've had a little bit of time on my hands to investigate it, it's pretty hard to say if there were medical centers in the old city. But if you recall, what we were mentioning last week as an essence of cities, of the ancient city, all the way through to the modern city, is that different specialties become localized in a city. So Uruk, we certainly know, had gardens and domestic spaces and temples, ziggurat, and the like. It's not, of course, clear whether there was medical specialties in Uruk, but such places, the idea that in a city you get these discrete functions that are spatialized in a particular way is an important continuity with the past. Also, and maybe this is going to be part ultimately of our definition of what civilization itself is that there is the emergence of these specialty tasks. So all the way from the earliest cities through to the contemporary, whatever we're going to call it, ecumenopolis, is the idea that you have these specialized skills associated with civilization and associated with the city. So when I'm here, I'm a patient, I have doctors, I have nurses, I have nutritionists, I have all of these good things that are nursing me back to health, for which I'm very grateful. So I guess a shout out to Evanston Hospital. But what I wanted to just record a few brief words for us about is where we left off on the last occasion, the idea of thinking about cities as systems. So city has these complex, spatialized, heterogeneous components that interact in a particular way that emerge to produce the functional whole of a city. And that is kind of empirical example of what we want to generalize here today, really, hopefully in the next 10 minutes or so, in thinking a little bit about the nature of systems in general. So where we left off, we had been looking at these different gradations of what we're now calling the urban hierarchy, all the way down from what we said, like isolated dwellings, all the way up to ecumenopolis, or at least to conurbations and to kind of these larger megacities and all of these sorts of things. And what I'd asked you to think a little bit about is, when you ordered them both in size of the entities themselves, but now also in the number of different types of entities that you find in any particular place, you get what's known as an urban hierarchy, or the settlement hierarchy. And this is kind of, maybe it's so obvious that it's not noticeable, but in any region you'll have a few maybe super large cities, conurbations, and then a increasing number of towns, small towns, all the way down. So it would be very typical for a large geographical area to have a central city, Chicago in the Midwest. Not that there aren't other kind of smaller cities in the Midwest, but there's one large urban area. But there's plenty of smaller towns, smaller municipalities, all the way down. And that pattern has actually been a source of frustration to both urban theorists and to economists, because here you have, and I want you to think about this a little bit, because it's sort of a rarity. This is a point that Paul Krugman makes in a paper that I'll post for us, is that it's pretty rare that you get a pattern in the world, whether in nature or in in kind of the human realm, where the pattern is extremely obvious, but the theoretical framework that you need to bring to bear to understand the emergence of that pattern is really complicated. Just a little footnote here, because just to kind of make sure that I'm getting this point across, that very often theory simplifies things, and the empirical world, the world that we see around us, is actually, vastly more complicated than the simplifications that our models and that our theories call for. But here's kind of the reverse. You've got this very simple pattern that seems to elude a very simple explanation. So we don't have to go into it in a huge amount of detail, but I'm just kind of reminding you here as well that these sort of patterns, these hierarchies in numbers, is also something that we see in the natural world. And I'm not going to argue that they are a manifestation of the same underlying pattern of the universe. But what I will say is that the habits of thought and the ways in which we orientate ourselves towards explaining simple patterns in nature and explaining simple patterns in the human realm, those habits of thought are things that we can share in common. So the way in which we think about problems, both in society and the way in which we think about understanding patterns of nature, we can think them together. And that's what I'm calling systems theory, is this unification of thought that allows us to think about complex problems. So just back to the urban hierarchy stuff for a moment. This is from the Paul Krugman paper. Some of you may know Krugman as a New York Times columnist. He's a Nobel Prize winning economist, and worked at and I think still works at Stanford. But I'm drawing here upon some of his academic work, because he wrote a pretty influential paper about 20 years ago on trying to understand the problem that we have in front of us today, urban hierarchies. Why do they exist? And what I love about this paper is that he admits that this simple pattern that emerges in the kind of physical nature of the spaces that we've built for ourselves eludes pretty simple explanation. Another thing that he does in this paper that I think is pretty important is that he says that the urban hierarchy is actually not just one problem. It's actually three problems that need to be understood. So when you want to come up with an explanation of why you get urban hierarchies, you have to ensure that your theory explains three things. One, just why are there, urban entities, towns, villages, cities of different sizes to begin with? Why are there some super large urban aggregations and some super small? The second thing you want to explain, and this is quite mystifying, is that the relationship between, so if let me put it this way, if you know the number of urban areas of a certain size in a region, you can make an almost perfect guess, a perfect prediction about the number of smaller towns, villages, and all the way down. And that's because, ever since there were cities in the US, which goes back, of course, well over a century and nearly 2 centuries, of course, at this point in the US, that it has conformed to this very simple pattern, and it's a pattern that is explained by something that is mathematically described as a power law. We'll get back to that, I think, in the class. It's not super complicated. Those of you who are kind of still keeping up with your math will remember what a power function is. But it's essentially kind of a prediction that, the entities, as you make a prediction about the number of towns, villages, hamlets, isolated settlements, that there is a relationship between the number of ranks, the number of different types of entities, and the total number of those entities that they're going to be. But let's get back to that. So on the one hand, you want to predict you want a theory that's going to predict the number of, the fact that there are cities and urban entities of different sizes. Secondly, you want to try and explain why this power law is so helpful in describing it and has been for at least a century. that pattern has persisted. And the third thing, and this is getting kind of maybe a little remote, is that the exponent in the power function that describes the relationship between towns, villages, etc., the exponent is very close to 1. So read Krugman's paper. I honestly don't, not that I think it's all that difficult. It's not necessary to have all of this under a belt, other than recognizing simple pattern, actually, 3 simple patterns that need to be explained by theory. The kind of delightful, frustrating part of Krugman's paper is that he reminds us, or at least he gives us evidence suggesting that we actually don't have a theory to explain this in the first place. Something else, I think, to which we'll return. But I wanted, rather than digging into some of these kind of complex explanations of, trying to approximate a theory of urban hierarchy, I wanted instead just for our remaining minutes is just to give you an introduction to systems theory in general. And remember what I'm trying to do here. I'm saying that on the one hand, you've got a pattern in nature, food webs. On the other hand, you've got a pattern in kind of human settlement, construction, and relative sizes of urban entities that seem to be similar to one another. They don't necessarily have the same underpinnings, but the way in which you think about both of these problems can be helped if you think about them both as systems. So, a few minutes on systems theory. There's a lot of different forms of systems theory, and I'm going to give us a definition of systems in a moment, but there's a lot of different types of systems theory. Some are developed for cybernetics, for communication systems, for social systems. I'm going to talk more generally about the one that's been developed for biological systems by Ludwig von Bertalanffy, although Bertalanffy, a biologist, ultimately intended his systems theory to be kind of a theory of everything, like a way of thinking, co-thinking across all of these different disciplines. I used to be maybe a little more enthusiastic about him. I'll just as a little biographical footnote, von Bertalanffy is clearly, he was kind of a complex character, always concerned about other people stealing his ideas, very prickly. What I hadn't realized until I had the leisure to do a little bit of reading from a hospital bed is that he was also a Nazi. There's that. I kind of don't know what to say. I'm kind of a little blown away by this, but he was signed up Nazi member from the late 30s in Austria, and of course he was kind of ultimately allowed to teach again. He migrated over to Canada and the US. He had various positions in the US before he died in the 70s. So I tell you that for what it's worth. Okay, so the essence of von Bertalanffy's thinking was that the old paradigm for explaining complex phenomena, whether it's urban hierarchies or food webs, these were not necessarily his problems, but complex understanding kind of complex entities was his problem. He was saying that the old paradigm is primarily one based on physics, which is what he calls a form of reduction. So it's a reductionistic way. So if you want to understand, let's say how a car works, you would look at the different component parts and make kind of generalizations about how those parts add up to produce the whole. And you can kind of think about that kind of reductive system as like a summative system. In that little diagram up to the right, those little white dots in systems 1 and 2. So the idea there would be that as long as you understand the component parts of a system, still haven't given a full definition of a system, but intuitively, if you look inside any complex entity, identify the component parts, and know enough about them, in theory, your explanation is going to derive from an understanding of those component parts. Whereas Bertalanffy was saying that for certain systems, particularly he had in mind these open systems, like living systems, that are kind of open to an environment, that very often it's very difficult to predict the functioning of the whole from an inspection of the constitutive parts. So constitutive systems are ones where the feedback between the component parts are actually driving the functionality of the entire system. And we already know, right, that ecology is kind of addicted to, or at least, too strong a word, but is kind of relies very heavily on systems thinking, because when we think about the Earth system, we already know that we divide it into these 4 subsystems. I'm betting this is familiar ground for most of you, but if not super complicated. We have an atmosphere, a biosphere, a lithosphere, the rocks, soil, and the like, and a hydrosphere. So von Bertalanffy's idea here, applied in this case here to the entirety of the globe, was that you could spend a lifetime productively examining the behavior of each one of these subcomponent parts. But in order to really understand how the global system operates, you have to kind of recognize that these subcomponent parts interact with the way that you get these surprising emergent properties. That's an important technical term for Bertalanffy, an emergent property. So, for instance, it would not be easy from just looking at the sub-component parts, atmosphere, biosphere, lithosphere, hydrosphere, to kind of recognize that our planet runs basically on two simple simple sets of exchanges. That there's an energy exchange. Every day we rely upon the sun to get up in order to give energy to the ecosystems of the Earth, but that energy flows. So the energy gets into the system and it flows through. We need the sun to come up every day. So we need this external source of energy that is pretty reliable. On the other hand, matter cycles, which means that there is a need for a constant exchange of matter. And here we're talking about carbon, nitrogen, oxygen, phosphorus, sulfur, etc., but we need kind of a exchange of those component parts in order for the system to work. And in fact, one way of thinking about the whole thing is that the energy flow, energy giving the ability of the planet to do its work, part of that work is the business of making sure that the nutrients flow in a way that all organisms are able to satisfy their material needs. Now listen, we're going to say more about it later, but I'm just giving you this idea that you can look at a system in terms of its subcomponent parts, but a lot of the properties of systems tend to emerge at the level of the complexity of the whole. It's a controversial statement, and we'll come back to it, but it is a pretty important one that von Bertalanffy and others would call holism or holism. So we've postponed our definition of a system, but let me quickly give it now. Each system is a entity composed of diverse but interrelated parts that function as a complex whole. Each part is called a component, and very typically at any one moment in time, if we're describing the state of a system, we're looking at the attributes of those component parts and the way that they interact at any one particular time. And you can probably already see, right, that if a system is any entity composed of diverse but interrelated parts, function as a complex whole, then hospitals and churches and gardens and homes, etc., the city with all of these heterogeneous spatialized components would of course be a paradigmatic city. It would be like a good example of a system, a paradigmatic system. So typically when you're drawing a system, and you can play around with this, you can think about systems that you're familiar with, whether it's your car or your computer, or I don't know, the Cubs as a sports franchise. You can break down any system into its subcomponent parts, right? And then look at the way in which those subcomponent parts interact to produce the whole. So I'm not sure that I can point at things here. I don't know how that would work, probably over like this. But each one of the, so there's a larger, outer box that is essentially the walls of the boundary of the system, and then within the system there are the subcomponent parts. Here is von Bertalanffy's insight on the left, that the whole may not merely be the sum of its parts. Sounds a bit like a cliche. It's also kind of something that we can complicate, but we're already deeply familiar with this. So for instance, if we think of the system that's drawn here as a water molecule, what's water? It's two hydrogens and an oxygen. And the idea here would be that you could spend the rest of your life looking at the properties of hydrogen, looking at the properties of oxygen, and not know that when these parts get together that they have properties like flow, or that, and this is a property upon which all life on Earth depends, that when water is solid, it's less dense than when it's liquid, so that ice floats. If ice didn't float, we would be screwed, and we can talk about that as well. The other thing I just wanted to put a kind of a flag in this, or is it put a pin, or I don't know what the term is, but it's something that we're going to come back to again because it's important, that a lot of the systems that we're interested in ecology at least, but also now that I think about it, just look at our example here, it's pretty familiar that most of the systems that we are surrounded by are what are known as nested systems, that there are parts within parts. So you take, for instance, a cell is composed of its organelles. The organelles kind of function in an integrated way to produce the properties of the cells themselves. The cells and their organelles are ultimately composed of atoms. The atoms are composed of nuclei, electrons, etc., etc. So, one way of thinking about this is that the universe is made of kind of a series of almost like, Chinese boxes, box within a box within a box within a box, all the way up to the limits of the universe. Now, there are certain systems that are, not neatly kind of hierarchical like that, and we can discuss some of those, but we can come back to that a little bit later. Another thing, again, just to kind of get your head into it a little bit, because it's super obvious, but then it becomes kind of almost thrilling when you look at it from a systems perspective, that when we're asking questions about the properties of any of the complex objects that we look at in the world. In this diagram here from Chris Langton, he calls it an emergent global structure. An emergent global structure here would be, for us, anything that we're particularly interested in that's a complex entity. It could be a city, it could be a car, it could be cubs, etc., etc. That very generally, when we want to understand the emergence of those properties, we look to local interactions of the component parts at the level below it in the system in order to understand how those properties emerge, right? So if you want to know kind of, why are you sick, right? If you want to know why you're sick, you'll go into the doctor, and the doctor, she's going to tell you that, it turns out that you've, I don't know, something wrong with your lungs or whatever. So she'll kind of describe to you kind of what's going on within the subcomponents of your system that are producing the emergent global structure, which in my case is nearly dying, but let's come back to that later. But do you see what I'm saying, right? That generally speaking, we want to translate our understanding of things into local interactions that occur at the scale below the one in which we are talking about. Now, you could keep going down lower and lower and come up with explanations. Arguably, this would be the ideal of reductionism, that you can keep going further and further and further down and reducing all of the objects of the universe to the way in which, I don't know my contemporary physics, but strings, something or other, quark, something or other, so you could get very remote from the emergent global structure that you're interested in and translate the problem into many layers below. But the strength of systems theory is that it allows you to kind of think about these kind of levels in the hierarchy understanding the way in which interactions that occur amongst the component parts, the interactions between them, the feedback between them, not just the properties of the component parts themselves, help you explain things about the world. So here, we're back again to our urban hierarchy, and it's not quite a neat kind of nested system, although of course large cities are often formed by the aggregation of smaller cities, and conurbations are very often the aggregation of larger cities and the like. But ultimately, somebody's coming in here, but ultimately, what we are interested then is in bringing a systems approach to understanding complex phenomena, both in the realm of nature and in the human realm that we create ourselves. So I'm going to just conclude with this. First of all, that the urban hierarchy, there's a real clear pattern without a very simple explanation. Look at Krugman for a little bit more detail on that, but we will put a little flesh on those bones when I get back. Secondly, we're saying that it serves as a example of a system. It's an example of a system. And systems theory, whether you're looking at von Bertalanffy's version of it or any of the other versions of systems theory, they're trying to formulate a very general approach that are robust regardless of discipline. So I can use systems theory to help me think about institutions interacting, or I can think about city structures, or I can think about ecosystems and the like. Objects that belong to different disciplines, but I can think about them in a very similar way. And finally, and maybe this is why I'm stressing the systems approach, is that we are going to take a very systems approach that allow us to think about cities as an integration of both kind of nature and culture, nature and social institutions. And just to give you a little flavour of that, I have a system diagram on the right from Stuart Pickett and his colleagues that kind of allows you to think about cities in terms of their human social system and then the ecological resource system that ultimately they're based upon. So thanks a lot. I'll see you pretty soon. I'll have another video up before too long. Hopefully this is helpful. I don't know, but we'll talk soon. Thanks a lot. Hey, and listen, thank you so much. So many of you reached out with lovely messages, and I greatly appreciate it. It really was very helpful to me. Thank you.